Okay.
All right, Jerry, you're on.
Good evening, everyone, and thank you for tuning in again. Our featured speaker is Mr. Zachary Covey, the meteorologist for the CBS 12 news team in West Palm Beach. Let me tell you a little about his background. While he was a student at Florida State University, Zachary developed a fascination and passion for weather, particularly tropical and severe weather. So he graduated from that university in 2016, not surprisingly, with a Bachelor of Science degree in meteorology. After graduation, he moved to El Paso, Texas, where he was the weekend meteorologist for the CBS affiliate there. 2 years later, he relocated to Myrtle Beach, South Carolina, where he worked for the ABC affiliate as the weather forecaster on Good Morning Carolinas. In October 2019, Zachary moved to his current position with CBS 12 in West Palm Beach. Zachary is here tonight, virtually, to discuss all aspects of forecasting the weather, including both the science and the technology involved. Coincidentally, the catastrophic hurricane that devastated Louisiana just 3 days ago makes his presentation particularly timely. So, Zachary, the microphone is yours.
All right. Thanks, guys. And again, I'm so sorry about last week with the technical difficulties, so thanks so much for joining us again. An amazing intro, so let's just dive right into it. And I can skip all of my intro because he did a really good job. He essentially covered all of it. The one thing that I do enjoy telling people, though, is I have covered a lot of hurricanes in my life. Hurricane Harvey, Hurricane Florence, Hurricane Dorian, Hurricane Isaias, and now with this past weekend, Hurricane Ida, doing a lot of work for some of our partners nationally as well. So it has been a very long weekend, and took a little break. Now I'm refreshed and ready to go. Apologies, I do have a minor cough today. All right, so we did go through some of these images last time, but again, I'll just kind of rattle through them. They are our studio here at CBS 12. We actually have 3 studios, but this is the studio you guys see the most often. A lot of different camera shots, a lot of different very cool high-tech looks that we can kind of use. We can put anything in any monitor. We can split it up, make it small, make it big. It is one of the most technologically advanced studios in the nation. So at least at a local television standpoint. So we are very, very lucky to have that studio. We also have 2 other studios. Like I said, they aren't nearly as cool as this one, but they're still really nice to actually have 3 distinct different looks. That is our CBS 12 control room. Again, everything that goes through our broadcast center, anything that hits your television screen, from our shows to the commercials to the newscast to my weather broadcast, go through this room. And we have access to national feeds, international feeds, CNN, AP, tons of different outlets that we work with nationally and internationally to try and get the footage and the video straight out to you guys. All right, so that's a little look at the station, but you guys brought me here to talk about weather forecasting today. So what is weather forecasting? First off, you got to look at the 2 terms, right? Weather, it refers to the condition of the column of air at any given point. Okay, this is something instantaneous. What is happening right now where you are, not only at the surface, but all the way through that column of air to the edge of space. Forecasting is all about using that process of estimation, guessing those unknown situations based off of what has happened in the past. So you look at the current conditions, you go back in past historical records and say, okay, these similar conditions match up with this day, so we can estimate this is what may happen down the line in the future. So the bottom line is weather forecasting is essentially predicting how the current state of the atmosphere right now will evolve over a period of time, whether that's minutes, hours, days, or weeks down the line. And again, the atmosphere is all connected. So when we talk about weather, we're not only talking about stuff here in Florida. stuff that's happening in California, Texas, or in a fantastic case, Louisiana with Ida, will impact millions of other people's down the line. For example, today, some catastrophic tornadoes were just about an hour ago on the outskirts of suburban Philadelphia. That came from the remnants of Ida. Catastrophic flash flooding is happening as we speak in West Virginia and upstate New York from the remnants of Ida. But that all came as the forecast from a system that impacted somebody else a couple days ago. So that's what weather forecasting is. And I'm sure everybody knew it. But how do we look at a forecast? How do we make a forecast? And in order to forecast out into the future, you have to be able to look at the base state or your current conditions. And there are quite a lot of different ways that we can do that. The first is looking at ground observations, or what we call Metars. These are thousands of boxes of little weather instruments scattered across the entire United States, all 50 states, including all of our territories, so Puerto Rico, Virgin Islands, and Guam. Now, we're not the only ones with Metars. So many other countries in the world do this, and that's how we can get a global network of data. But in the United States, we call them Metars. We can also use shipping observations. A great example of that is with Ida this week. We actually were able to record the strongest wind gust in that entire storm of over 170 miles per hour. And that observation came from a ship. It didn't come from land, but the ship was right off the coast. And so we were able to estimate that this was on the verge of Category 5 strength as it was making landfall. So shipping observations, very, very important. Aircraft observations are just as important. Yeah, we have the hurricane hunters, but we also have thousands of commercial airliners a day flying across the globe. Those observations go into our weather forecasting models, and we'll touch on that. We also use radiosondes. We'll talk more about what those are a little bit more in depth in just a second. I think a lot of people find radiosondes to be pretty interesting. Doppler radar, something I think everybody is familiar with at this point. They tune into the TV. You have a radar app on your phone probably. It may be a basic app, but it's an app. So everybody knows that Doppler radar helps to gauge rainfall, snowfall, but it's also helpful in a variety of other ways, and we'll talk about that today. Satellite imagery, that's also one other way. We have a lot of weather satellites up in space, probably more than you think. And we'll touch on that, and also we'll get you ready for the next generation of weather satellites that actually start blasting off this upcoming January. I'm going to take a drink. All right, so our ground observations. We obtain these ground observations across the US every minute. And this is what we call a Stevenson box, or a Stevenson screen, I should call it. And this is essentially what our Metars consist of. They consist of a variety of instruments within that screen. And if you're wondering why we put them in this box, we put it in the box because we want it away from the sunlight. Sunlight can contaminate raw data because if you're in the sun, you feel hotter in the sun. We want a raw temperature, a raw wind speed, a raw humidity value. And in order to obtain that, you must obtain that in the shade. And so what this box does with those little slits, it allows air to freely pass through the box, giving us an uninterrupted raw data view. So within the Stevenson screen, we have thermometers, measures temperature, hygrometers, that measures the amount of moisture in the air, psychrometers, it's another way to essentially calculate the wet bulb and the dry bulb temperature. That's more helpful for a couple of other things. A lot of people don't typically hear meteorologists talk about wet bulb, dry bulb. That's more for operational meteorologists to figure out where severe weather or snowfall events may occur. We won't touch into that because that tends to be pretty complex and can go over a lot of people's heads. I can tell you it went over mine in college there for a bit as well. Dew cells, it's another way of obtaining the amount of dew or moisture in the atmosphere. And a barometer, of course, measuring the pressure. Is the pressure rising, falling? And that can help tell us what pressure systems are approaching the area. Finally, we have a thermograph. These are becoming a little less common. They're becoming more digital now, but thermographs are actual graph paper that are thrown in this box, and it rotates very slowly, and you literally draw the temperature based off of, well, the current temp. So a National Weather Service meteorologist will go out there and change this every couple of days, and we'll have a raw paper backup. Nowadays, we're starting to go more digital with those. So thermographs are actually coming away, and we're just digitally recording the thermometer temperature in National Weather Service offices. So how do we obtain weather from over the water? Yeah, we can use satellites, but shipping observations give us a really good look at what's happening at the surface. For an example, with Ida, we were able to use satellite imagery to look down at the storm and estimate what the winds were before the aircraft, the NOAA hurricane hunters, were able to fly out there. But satellite estimates can kind of be a little fuzzy sometimes, especially when storms, not only tropical in nature, but just everyday storms, it can be a little fuzzy. Shipping observations are literally ships going through these systems. They are giving us the raw data on the ground. So they are very, very helpful. These observations went back to the early 1900s. Ships across the EPAC, or the Eastern Pacific, we call it, would report back these weather conditions, and it actually would help us, before the satellite era, forecast what was coming on shore. Because we know in the United States, and mainly in the Northern Hemisphere for the most part, weather moves from west to east. So those shipping observations in the Eastern Pacific were super helpful in forecasting what Pacific storm systems were rolling on shore and how those would evolve over time as they march their way across the United States. Could it create a tornado outbreak in the Midwest, or Tornado Alley? Could it bring a devastating, crippling ice storm to parts of North and South Dakota? Or could it actually lead to a flash flooding event in parts of Tennessee or the Carolinas? So the shipping observations back then were super crucial. And still today, they are more used as data verification, more so than forecasting. Like I said, we utilize satellites a lot more for that forecasting, but the shipping observations give us more so a data verification of, yes, what the satellite is saying is correct, or no, what the satellite is saying may not be correct. So it's not mainly used for forecasting anymore. It's more used for data verification. Now, aircraft observations. We think of the NOAA hurricane hunters, the Air Force Reserve hurricane hunters at the 53rd Weather Squadron. But we've got thousands of commercial planes, right? All around the world, every single day, taking off, flying places. And each of these aircraft have the ability to record weather. In today's forecasting era, that is literally hundreds of thousands of weather reports going into our forecast models every single hour. Now, since 1998, all commercial aircraft, and this is universal, are outfitted with something called AMDAR, or the Aircraft Meteorological Data Relay. And so what this is it's a sensor that sits on the outside of the cockpit, and it relays live weather data instantaneously to ground stations. Now, that data will include air pressure, air temperature, wind speed, turbulence, and humidity values. Now, we don't really get wind direction because when you're going at a speed so quickly, it's a little difficult to necessarily tell where it is. But if you're caught in the jet stream, we can easily tell where that is because the jet stream tends to speed up a whole lot faster than the surrounding air. So we are actually able to tell that. Now, radiosondes. This is my favorite part, and I think a lot of people love these radiosondes. You see that white balloon there, and this is a National Weather Service meteorologist launching a radiosonde into the atmosphere. So since weather is a dynamic process, it uses the entire column of the atmosphere, right? We need to survey not only what's happening at the surface. Metars, shipping reports, those are great. But what's happening 5,000 feet above our head, 10,000, 20,000 feet? We don't deal with it here, snow, but in the Northeast, that's really important. Where's the freezing level? Is the freezing level high enough that as those snowflakes fall, they're going to melt into rain? Or is the freezing level so close to the ground, but not actually at the surface, that as those snowflakes fall and melt, they don't have enough time to melt, and they may actually fall as freezing rain. That is really, really difficult to tell, and radiosondes can help with winter weather. It also helps with a variety of other things. Hurricane forecasting, for example, it helps to determine the upper level flow, which ultimately drives where a hurricane is going to go. Where are the highs, where are the lows, and where are those weaknesses that the hurricane is going to feel and eventually move to. Now, radiosondes can provide that look into the atmosphere above, like I said, and these sondes are launched twice a day across the entire United States, all NWS offices, and across our territories as well. Now, sometimes NOAA, the National Weather Service, Hurricane Center, Storm Prediction Center, they may need a bit more data than just twice a day. And they may relay to certain Weather Service offices, hey, can you go launch another balloon for us so we can get that data? Maybe, you know, instead of waiting 12 hours, I want data every 6 hours. So they can go out and do a special balloon launch. So what is at the bottom of that balloon, right? What is at the bottom? That is the radiosonde. And that's what it looks like. Get a good look at this picture. If you see on the side, it says Harmless Weather Instrument. And that's because a lot of people see these because they do float back down to Earth. And they freak out. They don't know what it is. It is a harmless weather instrument. So you don't need to freak out if you ever stumble upon one of these. But they're small instrument packages that are suspended beneath this balloon that is filled with either hydrogen or helium. It depends. I went to Florida State. We picked obviously the non-flammable gas because God forbid something happens. We don't want to blow up our campus building. So different weather service offices will use different gases to launch these. But as the radiosonde is carried aloft, it's going to measure pressure, temperature, and humidity at all levels of the atmosphere as it goes up. Now, these balloon launches are also linked with a battery-powered radio transmitter that sends that data in real time, in live time, back down to the ground receiver. And with the GPS sensor, you may notice there's no way that we can record wind, but we know where we launched the balloon, and because it's in live time, we know where the balloon is. So through a mathematical equation, we can not only figure out the wind direction, but we can also figure out at which the speed this balloon is traveling, which gives us the wind speeds at various levels within the atmosphere. That's why meteorology tends to have a lot of math associated with it. Now, these flights, these balloon flights, they can last up to 2 hours long. It can take that long to go through the entire column of the atmosphere, right up to the edge of space. But once the balloon pops, that zone is going to parachute back down to Earth. Now, one fact about that balloon, by the time it reaches the edge of space, right before it pops, it's going to be about the size of a 2-story building. So think of a 2-story well-constructed home. That's the size of the balloon that's carrying this tiny little radiosonde package. Because as air pressure decreases aloft, the air is going to expand within the balloon, and the balloon is going to expand to that incredible size. Now, these packages can be used multiple times, and that is why we outfit them with parachutes. Now, most of them, unfortunately in Florida, land in the water. We've got the Atlantic, we've got the Gulf, we've got Lake O, and we've got tons of rivers, streams, lakes around us, and the Everglades. So you may not find them here in Florida, but in the Midwest, you can find these radiosonde packages, and that is why it says harmless weather instrument on it, to kind of keep people from worrying what it is. It also comes with pre-packaging. So if you do find it, you can put it in the pre-package and drop it in any USPS mailbox, and it'll be shipped back to the Weather Service, and they can use it again. Excuse me. Doppler radar. That's what it looks like. You've probably seen these before at airports. National Weather Service offices have them. And this came about back around 1950, 1946 to be exact. The US Navy was getting rid of 26 of their aeronautical radars, and they decided to give them to the Weather Bureau, which is now NOAA. And the Weather Bureau said, yeah, we'll take them, we'll do some maintenance on them, and we'll outfit them to become used for meteorological purposes. And the first one, known as WSR-1, was deployed at Washington's Reagan National Airport, which is right outside of DC. the National Mall, the White House, all that stuff. So that's where the very first weather radar was deployed in 1947. Now, today, the National Weather Service operates 159 of these next generation radars, or what we call NexRad. Now, they're across all of our states, all of our territories, but we don't actually cover the entire US. There are actually some radar gaps in the United States, some areas that have no radar coverage whatsoever. Now, the National Weather Service actually has strategically placed the radars in areas that mainly people live. So these radar gaps are mainly very rural areas out in Wyoming, Montana, Idaho, locations that may not have thousands of people. It may house, quite frankly, 10 people in a population. Now, these NexRad radars, are top of the line, but we knew that we could do more. And recently, we just brought all 159 radar sites up to date with the new dual pol technology. We literally just completed this across all 159 radars last year, I want to believe. Was it last year or the year before? But this has been going on since about 2015. It has been a long, long process. So what is dual pol? Why do we care about it? Well, prior to the development of dual pol, essentially radars send out one beam and one beam only. It goes out and it comes back. And what that does is it tells us the size of the particles, but we're lacking a lot of key information. So what dual pol radar does is it sends two pulses. It sends a vertical pulse and a horizontal pulse. And if you get what I'm going with when I say that meteorology has a lot of math, knowing the size of the return of the vertical and horizontal pulse, we can throw those into mathematical equations that can give forecasters a suite of more in-depth forecasting data, especially times during rough weather. For example, we can detect where a tornado may be based off of the debris signatures that we can see in the air. Before, with dual pol, we would have never been able to detect debris, but now that we can estimate the size of the particles with both the vertical and horizontal beam, we know the size of raindrops and snowflakes and hailstones. And if we're detecting something that is none of those sizes, we know that it is a foreign object and it's not meteorological. And typically that would be debris. And that actually helps forecasters now issue more accurate tornado warnings and in a more timely fashion. So dual pol is really, really helpful for that. It's also helpful for a suite of other things like snowfall and hail. This is what I'm talking about. When I say it sends out a beam, you can see the horizontal beam in blue and the vertical beam in purple. And so you can see how a raindrop varies from a snowflake, varies from a hailstone. And so when you get those nasty winter storms in the Northeast, where the rain snow line is so crucial on determining if you're going to get 1 inch or 10 inches of snow, this can become a very, very helpful signature. Also, like I said, with tornado debris, you can see the radar reflectivity. This is the same image here. Radar reflectivity on the left, telling us where that heavy rain is. Radar velocity is telling us where the wind speeds are and the direction they're going. Green is towards the radar, red is away from the radar. And so where that couplet is that we've circled, that indicates an area of localized spin. And it's also co-located with something we call correlation coefficient, which is that tiny box in the bottom right. And that's telling us that little green, blue, purple dot, that's telling us that we are detecting something that is not meteorological. Whatever is being detected by the radar there is too large to be rain, snow, hail. It's likely debris of some sort, whether it's trees, power poles, shingles, roofing, siding, something non-meteorological is flying in the air, and we can issue a tornado warning. To really hammer it in, here's what the radar looks like. 1961 with Hurricane Carla to Hurricane Michael in 2018. It's just drastic to tell the difference between the initial radars we had to today's dual pol technology. You can see the convex banding. You can see the eye wall in Hurricane Michael. You can see the eye wall in Carla, but it's all white. So you can't tell where the lighter rain is versus the moderate rain versus the really, really heavy rain. Michael, you can easily determine that. And finally, with satellites, this is our last way of determining current weather. So on April 1st, 1960, NASA sent a rocket carrying the satellite you see there on your screen. And this satellite was called TIROS-1. It was the very first polar orbiting weather satellite. Now, TIROS-1 was not expected to do great. A lot of people had a lot of speculation if it would even work. Would this be able to help weather forecasting? And there was a lot of quite frankly, fear that this wasn't going to work and this was going to cost the Weather Bureau and NASA a lot of money. But a couple days later, TIROS-1 sent the very first image of what clouds look like from space. And it was the start of using this satellite imagery to forecast the weather down the line. Now, TIROS-1 only had 2 ground stations. It flew 450 miles above the Earth, and it only had 2 command and data acquisition stations on Earth. So unlike today, where we can be in nearly constant contact with just about everything in space, you had to wait for that satellite to pass by one of those stations. And when the satellite did, which could be hours between passes, all of the images that that satellite took since its previous pass were recorded on 35mm film. So this is completely different from what we do today, where you can literally look up satellite on your phone or on your computer or watch it on TV nowadays, right? So this is completely different. However, even though that TIROS-1 only operated for 78 days, it was considered a huge success by the Weather Bureau. And this started the kind of snowball effect of building weather satellites and launching them into space. On the left, that is the very first image that TIROS-1 sent just a couple of days after being launched. And a few days after that, it sent the image on the right of a typhoon that was east of Australia that literally nobody had any clue was coming to Australia. And so that actually proved that this was a big deal. We can literally look at weather that we have no clue is about to impact a country, a state, a province. This was a huge success. And that's why, even though it only operated for those 78 days, it was a major, major plus and milestone. So today's next generation satellites, well, NOAA owns 9. 4 of them are geostationary, which means they move with the Earth. So they're constantly looking at the same spot on the Earth at all times. 4 polar orbiting satellites, so they orbit the poles. So they're constantly scanning a new place on Earth. They will scan the entire Earth about twice a day. And the Discover satellite. Now, like I said, geostationary moves with the Earth, so they're constantly in the same place. We talked about what polar orbiting satellites are. And again, that can be really helpful in with climate forecasting, how the climate is developing, changing, especially with climate change. And then Discover, this is the one weather satellite that I don't really use, but space weather forecasters do. It's 1 million miles away from Earth. It's parked, it's not really moving, and it's aimed towards the sun. This satellite actually helps warn about harmful space weather like coronal mass ejections that can mess up satellites, GPS, radio technology, and then also can help forecast the Aurora Borealis or Aurora Australis, the southern lights. So there's a map of all the satellites. The blue ring, all the satellites on the blue ring are geostationary. The red rings, are those polar orbiting. And that yellow one all the way out there, that's the Discover satellite that's staring at the sun. Again, it's not only NOAA. We also have partners with EU METSAT, with the European Commission, with the European Space Agency, the Department of Defense, and so many national and international partners. So GOES-R is our current weather satellite up there. This is considered GOES East right now. And this is what looks down at us here in Florida. This is the one that's positioned over the east coast of Florida. In 2018, they launched GOES-S, which then became GOES-West. However, just days after launching GOES-West, it actually ran into a malfunction with a loop heat pipe. You don't need to be a satellite engineer to realize that sounds kind of bad. Basically, the spacecraft cannot cool itself down in the summer months. And so as a result, The Advanced Baseline Imager, or ABI, that's the camera that takes the photos of the satellite or of the Earth every day. During sunrise and sunset, during Northern Hemisphere summers, it will just mess up. You're not going to get any data, and it's going to be like that for about 2 hours. So we are about to enter Northern Hemisphere fall, and that's going to start to subside, and we'll get data again for 6 months. Now we are slated to launch GOES-T and then GOES-U. Those are the next two satellites. They're the same build. They did fix the loop heat pump on both of these, so we won't run into this issue again with these new satellites. But once GOES-T launches in January 2022, it is expected to become GOES-West, so we can move that satellite that still has that issue into kind of like a parking orbit as a backup, just in case something goes wrong with one of those two satellites. We'll have that in a parking orbit for a backup. But this is what those satellites look like, those R, S, T, and U. You can see the solar array, the ABI, the Advanced Baseline Imager on the bottom. That's the camera that stares down at the Earth and takes those photos. But it's also outfitted with tons of different equipment. My personal favorite is the GLM, the Geostationary Lightning Mapper. It is our first attempt to forecast lightning from space. And let me tell you what, since 2016, it has been miraculous, the lightning data we are getting from space. And it's actually helping forecasters forecast where severe weather is. That is an image from GOES-East. Look how crisp and clear that is. Compare that to the TIROS-1 satellite that you saw earlier. It's just night and day, right? So GOES-R will scan for these high quality satellite images every 5 minutes. TIROS-1, you had to wait for it to pass one of the stations. We get these data every 5 minutes now. It also has two mesoscale sectors, which can look at a small portion of the Earth and refresh that image every minute. Now, if you put both of those mesosectors over the same area, you can get live satellite data every 30 seconds. And like I said, it's also outfitted with that state-of-the-art geostationary lightning mapper, which is just super helpful in identifying developing storm systems along fronts, for example. It also has that suite of space weather that I told you about. So now that we know how we forecast essentially our current conditions, how do we use that and move it into the future, right? Forecasting the weather takes a suite of technology like supercomputers that you see on the left-hand side. This is known as numerical forecasting or computer modeling. This is where we take everything we have, throw it into a computer and say, solve these insanely hard mathematical equations. They are so difficult, your desktop computer won't use them. No math whiz in the world can sit down and solve it. These computers are simply made to take raw data, run them through insanely long mathematical equations, and create a graphical forecast, either hours, days, or weeks in advance of what the state of the atmosphere may look like. Now, these supercomputers will look at air pressure differences, solar radiation on Earth. It's not only looking at the temperature and the pressure and all, it's taking into account the Earth's rotation, the current water cycle of where you live. How is the water cycle affecting your current conditions, right? And so when it takes all of that into account, it spits out images like this. This is 2 meter maximum temperature, so AKA your high temperatures for the day at any given point. And so in this case, you can see a huge cold pool along the Appalachian chain, temperatures in the 40s there, 50s in North Carolina, upper 50s, low 60s for South Carolina. You head down towards the Panhandle, they're sitting in the lower 70s. This is a sample image of what the radar may look like. You can see the intense rain bands across parts of New Jersey and eastern Pennsylvania, back out through the Great Lakes, moving into upstate New York with lighter rain spreading in from Massachusetts up through the Cape and over towards Portland, Maine. This is the European model. This is looking at forecasted wind speeds of a hurricane. In this case, this was Irma back, I believe, was that 2017. And you can see those really dark colors around the center indicating major hurricane strength, category 3 strength. So there are a couple of different types of models. There's stuff known essentially as global models. And global models are models that look at the weather pattern over several days or a couple of weeks, 10 to 14 days. These are going to be things like the American model. the European model, the Canadian model. People know these, especially during hurricane season. What's the American say? What's the Euro say? These are known as global models. They go out that long span of time. But you also have mesoscale modeling. So these are high resolution forecasts. For example, the image you see on your screen is considered a mesoscale model. It's very high resolution. You can see where the line or the squall line is moving through the mitten of Michigan into parts of Madison, Wisconsin, south, right, working its way towards Chicagoland. But mesoscale models, because they produce a higher resolution image, they only have a shorter time frame that they can work on. So these mesoscale models, like the NAM, like the RPM, like the graph, like the HRRR or HRRR, those will only go out 12, 18, maybe 24 hours. So you get really high resolution precision, but you lose your data points, your data time essentially. So what is next? What's coming down the pipeline in the weather community? Well, the continuation of improving these forecasts are going well beyond the 2020s. The National Weather Service, NOAA, they've realized, especially with what we've seen in the Space Department, right, with agencies like SpaceX, Blue Origin, that cooperating with the private sector helps a whole lot. And so the National Weather Service and NOAA are cooperating with the private sector to bring those new technologies out to the forefront to get us thinking about what we can use tomorrow. In broadcast television, weather vendors like IBM, they're the ones that supply our data at CBS 12, are creating high resolution modeling of their own. And so this is bringing better high resolution forecasts to broadcasts, to your screens. And so you can rely now on your local weather station to give you a better forecast than whatever your phone app may say, because your phone app is just reading the raw data output from any of those computer models. Those render out 4 times a day. So 4 times a day, that forecast is going to change. Whereas with those high resolution models, your broadcast may stay pretty consistent in their forecast the entire time. And finally, in academia, universities are gung-ho on working on climate change research, right? Polar orbiting satellites are really helping. Shipping reports are really helping. We're taking research ships up to the Arctic, also down to the Antarctic, and studying, the water cycles, the unfortunate melting of the polar ice caps. And how is the melting of those ice caps and the addition of more water into the oceans going to impact forecast modeling skill and accuracy down the line? Are we going to actually increase our skill, or could the skill decrease from computer models? So that's something academia and universities are using at this point in time as well. So there's a lot of new technologies out there that are coming down the pipeline that people are working on, and it's a really exciting time in the meteorology and even climatology world as well. Although I'm not a climatologist, that's a whole different story, but it is a very exciting time. So I want to say thank you so much for having me, and I'm ready to take your questions.
Well, Zach, thank you very much. That was very interesting. I want to ask you a question. Did you by chance get a copy of the questions that I emailed you?
I did. Let me.
Okay, but let me, before you do that, you had said to me in our email conversations that you could help us understand, and you mentioned it in your presentation. I would say almost all of us have a weather app or 2 or 3 or 4 on our phone. Mm-hmm. I know I, for one, and probably a lot of people listening, we play outdoor sports, golf, pickleball, tennis, and I rely a lot on, I'll just use a brand name, WeatherBug. WeatherBug happens to give me local lightning. I'm a little more concerned about getting lightning hit than I am about a bunch of raindrops. So can you just go over, before you go over the questions, how all of this technology could help us look at our weather app and what we should look at so we can be better informed and prepared both for local sports and or just going for a walk and or Mother Nature's terrible storms, what we should watch for and what we should be aware of, that we may learn how to read these apps or these high-res forecasts better. I'm not quite sure I explained it right.
No, you're right. And, you know, the basic kind of premise, and I think everybody learns this from a very early age, right? The worse the color, The darker the color, the heavier the rain, or the heavier the snow. And we all learn this in elementary or middle school, you know, when we do our weather segment in 6th or 7th grade. And I think everybody has it down to that point. But, you know, you bring up a really good point with lightning. And nowadays, unfortunately, lightning data is becoming more and more a premium feature in a lot of weather apps. There are a lot of companies out there that realize, like you said, they're more concerned about getting struck by lightning than if a heavy rainstorm is going to fall on their head. They've got an umbrella, they've got a rain jacket, they can bolt to the car from the grocery store. It's fine, it's rain. And so a lot of companies are starting to go that route. Now, WeatherBug has not, like you said, so far, WeatherBug has stayed that way. And so I think when you read these weather maps, they're always going to come with a slew of different information, especially nowadays. There are thousands of different weather radars on your, you know, App Store, Google Play, whatever it may be that you use. The only thing I think everybody needs to take away from these weather apps is knowing where you are. And that's the biggest thing, is knowing where you are in relation to your home or your business, because a lot of people don't read mapping well. I can talk to so many people and say, what county do you live in? And they're like, Palm Beach. Okay, well, point it out to me on a map. And you'd be surprised how many don't know where that is. So the first thing I always do with them is always turn on your geolocation. Always hit that little arrow, and it's going to put a dot right where you are, so you know exactly where you are in relation to everything around you. That is the most important thing. Second off, before you animate it out, before you look at that futurecast that WeatherBug or Weather Channel app may have, or CBS 12 Weather app, you know, look at what is happening around you. Okay, I've got a shower to my west, I've got a shower to my north, but I see it's clear to the east and to the south. So as you play through it, you can start to see visually those weather patterns, those west winds take over, and see that shower advance over time. Now, keep in mind, these weather apps, like I said, update 4 times a day. They update with every global model forecast that comes around. So that's going to be 0, 6, 12, and 18 Zulu. We, in the meteorology community, utilize Zulu time or mean Greenwich time, which we're only 4 hours behind. So for 0Z, that would be 8 o'clock. We're approaching 0Z right now. Your weather app is about to update. And so if you look at it earlier in the day and you see something, and then you look at it at 8 o'clock and it's just not there, you got to keep in mind that your weather app isn't interpreting necessarily how the day has evolved. It's just taking raw model data and spitting it out to you. So always take those future casts with a grain of salt. And that's why I always recommend you download a local weather app, because local weather apps are actually controlled by your local meteorologists who know how the weather is going to evolve throughout the day, because we look at the raw models, but then we edit them based off of our knowledge of how the local viewing area, how your local DMA essentially is, you know, evolving. Do you have a warm pocket in Jupiter typically? Well, we know that it's probably going to be a couple of degrees hotter than what the computer models are saying. So I know a lot of people like Weather Channel, WeatherBug, stuff like that. But if you go to those local apps, you're more likely going to find a more accurate forecast for your area.
Well, I want to give you a plug. Yes. Since you and I talked, I downloaded your CBS app, which I had on my phone, but I hadn't used in years. And it was great. You had an incredible number of local variation maps, and I found them great. I only mentioned WeatherBug because it's the only one I found that really gave me my lightning forecast when I'm playing my outdoor sports. With that in mind.
Like I said, lightning data with WeatherBug, that's one of the reasons WeatherBug continues to be so used. People have that simply so they don't have to pay for lightning data on the Weather Channel app or another app.
I want to give everybody a plug that your CBS app is outstanding, and it's got a tremendous amount of local data. With that,
thank you.
That was great. Thank you. You can either choose to answer the questions I emailed you first, or take a look at the Q&A, and a couple of them are redundant of the questions I sent you. But I'm going to start off because Jerry asked this, a very interesting question. That's the guy who gave you your introduction. Climate change has been very interesting. We know about cloud seeding, and we know we've got droughts, fires, all kinds of unfortunate weather circumstances. His question was really pretty simple. With climate change going on and cloud seeding having been shown to be relatively successful, how come they don't tend to use it more to try to fix some of these issues with droughts and forest fires? Is that pretty close to what you said, Jer? Okay, I got a nod, so go right ahead.
So cloud seeding is pretty successful in some areas, and that's pretty much your answer right there. We have tried to cloud seed in some arid areas over in the Middle East, the Saharan, or out there through the Saudi desert, for example, and it's just too hot and too dry to actually develop the cloud seeding that we are looking for. Now, we have successfully cloud seeded in parts of the Pacific Southwest, the Four Corners region. So I think the answer to that question is it's partially successful in some areas. The other side of that coin is it's also really expensive. It utilizes silver iodine, and silver iodine is not a cheap chemical that we can throw up in the air. And before we say chemicals in the air, and I know some people may say you're throwing chemicals in the air, it is completely harmless. Silver iodine doesn't have anything that we need to worry about to us humans or even to the animal life, which is good. But it is also very expensive, and that can come out of the taxpayer pocket. And so ultimately, when NOAA submits their budgets, that goes through the whole political ring of trying to figure out what's staying, what's getting cut. And a lot of times, because it's only so meso-focused, it's not going to help necessarily the entire country. It's going to help a very small portion of it due to the cost versus the effect to help X millions amount of people, that can get cut. And so that's kind of the reason why. It's kind of a battle between how many people does it help and what's the cost for it.
I know since we're in hurricane season, let me jump to two questions that came up. One, you mentioned tornadoes. One person asked, they live in the Midwest, and it seems like their tornado forecasting is pinpoint on, and they've noticed that in the South Florida, we don't seem to pinpoint tornadoes as accurately or down to the street level that she was used to in the Midwest. Was that a misstatement on her part, or is that somewhat accurate, or how can we look at tornadoes because they seem to be more prevalent? I think one just went through Philadelphia or something, you said at the opening of the presentation.
Yeah, well, to be frank with you, South Florida doesn't really get a lot of tornadoes. On average, our area, which would be essentially from the Treasure Coast all the way south through the Florida Keys, outside of landfalling tropical systems, which can produce tornadoes with these landfalls, we average about 7 to 10 tornadoes a year. So that is exceptionally lower than any number in Tornado Alley, any number in the Midwest, and any number in Dixie Alley, which is essentially Alabama through Georgia up through the Carolinas. So I think I understand her question, but I also think we just don't pinpoint those tornadoes down to the street because, quite frankly, we don't get enough of them.
Right.
Yeah, we don't need to. Now, water spouts are a different animal, and we get quite a lot of those, especially in the wee morning hours. But those tend to fizzle out before they ever hit land, and you guys never really hear of them. Unless you're up super early, you're probably not going to care about a water spout. So, yeah.
Two other questions came in. One is going to be about climate change, which you sort of talked about. Maybe you can talk about how that's impacting the weather change. But given the local thing that happened to Ida and went through the Gulf, it seems like South Florida has been spared over the last couple of years, and the Gulf has gotten creamed. Any reaction to that sentence? And do you think that's a trend that's going that way?
It is true. I don't know how deep in this answer I want to get. There's something known as the long-range cycle.
Keep it at the satellite level.
There's something known, excuse me, something known as the long-range cycle, and it recycles every October. So essentially, globally, there are a number of high and low pressure centers that develop across the globe and they work their way around the globe, and it takes around 40 to 45 days to work their way across the globe, and they'll repeat over the course of a year from October to October. Last October was when we started seeing Laura, Delta, Zeta, Eta hit Louisiana. And so we knew that there was this long range cycle of an upper level low that was constantly feeding a tropical cyclone there. And sure enough, Ida, believe it or not, is the recycling pattern from Hurricane Delta last year. It's the same upper level low that created Delta last year. Now, there's a lot that I can go in on that, and I'm not going to, but it wasn't a surprise that we saw that. We actually were able to forecast that during last weekend, Louisiana had a threat for a hurricane. We forecasted that back in March. So that tells you how good this long range cycle goes. Now, with that said, long range cycles, like I said, recycle every October. So we're about to reach the end of this cycle, and we're not going to be able to reforecast these LRC patterns until maybe about January, February, March, because we got to look between October and January. Where do these highs and lows set up? Where are these patterns occurring? And then we can use forecasting techniques and timing techniques to estimate where they'll be again. So does Florida have a threat come October, November? It's possible. We can't tell you necessarily with the long range cycle. I will tell you South Florida does have a minor threat at the end of September. Now, is it going to develop? It might not. It may just be a really rainy weekend, but it is a period that back in March, we forecasted a low pressure center moving through South Florida. So there's a lot of other factors that go into necessarily developing it. We've seen how this hurricane season has gone, so we always want to be prepared.
Two other questions on the same topic came in. Sort about forecasting. Several times the local forecasters said, oh, you're going to get a few inches of rain. The next thing you know, you get 18 inches. I know everybody says that as soon as the weather forecaster says X, it's Y. But jokes aside, with all the stuff, with the technology in the background, has it gotten harder, or is it really very hard to predict how much of volume of wetness you're going to get? Not counting.
Well, that's fair. Like I said at the very end of the presentation, one of the things in academia, colleges, universities are researching is how is the water cycle changing due to climate change? Because as the polar ice caps melt, yeah, we put more water in the ocean, but ultimately we know the water cycle, right? Water evaporates and creates clouds, and they rain out and they accumulate, and you get the cycle. So with more water in the atmosphere and in this water cycle, how are global forecasting models, how are mesoscale models reacting to that? And that's actually something that we are researching, and quite frankly, we don't have an answer just yet. This is something that they've been doing maybe for the past year and a half. It's probably going to still be a couple of years before we have a really true defined answer that we can get behind. With that said, I will say forecast accuracy with the computer models right now are around 88 to 92%. We did take a slight dip during COVID, during the initial shutdown period that the entire globe went through last year. And that was actually because so many flights, as we all recall, were grounded. Nobody was flying. And because so many thousands of planes across the world were grounded, our forecasting skill actually took a hit by a couple of percentage points because we weren't ingesting as much aircraft data. So those numbers have gone back up. We're around 88 to 92% accuracy globally with forecast models. But that's a really good point. How is the water cycle going to impact these down the line? Could we see that dip again with climate change? So I wish I had an answer for you, and I just don't yet. But in a couple of years, we're hoping to have a better look. And if it is, in fact, taking a dip, how can we rectify that? Do we need to upgrade our computer model somewhere? Do we need to tweak those mathematical formulas to account for higher water vapor? How do we up that accuracy? So that's something that'll come down the line.
That's great. All right, those were, I think, a summary of the questions that had come in before. It says, what happens to the observation ships when a hurricane comes through?
So we try our very, very hardest to not sail ships through hurricanes. We've seen way too many disasters over the years. So we really do try to avoid them. Major hurricanes, you're never going to find ships around them. Now, you may find ships in port, which, for example, with Ida, I told you that we had a shipping observation that recorded a gust of 170 plus. It was the highest gust. That ship was in port. It wasn't sailing. It was not going through 40-foot seas and winds of 140 sustained, gusting to 170. I think that captain would have literally lost his or her mind, if they went through it. So we try our hardest not to do that. But there will be some ships in tropical depressions, tropical storms, weaker systems that will go through it and relay that data. But most shipping observations in hurricanes are going to be from ships that are keeping their weather sensors going at docks, or maybe they're docked, anchored just offshore, close enough that the waves aren't going to necessarily ruin the ship, but still a little farther away that we can get a really good offshore measurement.
Great. And in two questions concurrently, is there public access to U.S. weather radar available? Let me rephrase that. In real time, do we have access to U.S. weather radar?
Yes. Weather.gov. If you go to weather.gov, I could actually, I don't want to steer you guys in the wrong way, but weather.gov is the official website of the National Weather Service, of NOAA. And if you go there, right at the top of their page, they're going to have a big banner that normally is talking about the big weather headline of the day. But right below that, they have a tiny menu bar with little blue words, and the third one says radar. That is live radar from all 159 NEXRAD dual pol radars across the United States, Alaska, Hawaii, and our territories. So you can look at radar in Puerto Rico, in Hawaii, in Guam, and of course, all across the United States, and it updates in real time.
That's very cool. So I imagine that you guys, with all your sophistication, take that data and you said manipulate it to the local area?
Exactly. We get radar through our weather vendor, IBM, but it is the same radar data. All of that radar data, whether you get it from NWS or NOAA or through a weather vendor like Broadcast Mets do, they all originate from those NEXRAD radars. So it's all the same data stream. They're just different vendors that are supplying it.
All right, this is a trick question. What has been the most accurate model to forecast hurricanes in Southeast Florida?
A lot of people are going to say the Euro. I am going to tell you this year, it has been the American, and not even close. The American went through a $1 billion upgrade last year. We put so much money in this. And this was the first, I guess we tested it a little bit last year, but this is the first full hurricane season that we're utilizing the American with its new upgrade, the GFS V16 upgrade. And it has been dominant. The European has corrected and corrected and corrected time after time again. The American has held steady, steady, steady. And so far this year, the American's done really well. So could we be seeing a flip down the line? It's possible, but a lot of people will still, I highly recommend this. Don't always focus on just one, right? It's a blend, because most models aren't always going to be accurate. So you need to blend. What is this model doing? What is this model doing? What is this? And then create a blend. That's what the Hurricane Center does. That's what I do.
In your app, what would you think would be the best section for us to go to if you were to announce that it looks like Ida is coming towards Southeast Florida? Which one of your radar models on your app would you suggest we look at most closely?
If that were happening, I would not direct you guys to models at all. I would direct you to your local broadcast Mets. And the reason why is because with local forecasters, local Mets, we know areas that are susceptible, more susceptible than others. So you may look at a model and see a 120 mile per hour wind gust in Wellington. We know Wellington is far enough inland that is highly unlikely, unless it is a top tier Cat 5 hurricane. And so knowing that, you guys may look at the model and freak out, but we would know that, and we may actually physically bring those values down on our broadcast or our website, and we write web articles, we do Facebook Lives, we do Twitter, we do obviously television. And we will localize those impacts for everybody, because the barrier islands are going to feel something different than the coast of Palm Beach, than the coast of Vero Beach, than Wellington, than Okeechobee. And so knowing your local meteorologist in those hurricane days, right, listening to them, you're more likely to get accurate and more timely data for you and your family than looking at any forecast model.
So to repeat what you're saying, with the Twitter apps from CBS or the CBS weather app, I mean, sometimes we'll lose our TV. So if we don't, what I was getting at is if we don't have our TV and we're relying on our appliance, where would you suggest we go so we can sort of keep up to date with whatever is happening to the best we can?
So if that ever occurs, let's say it is a landfalling system and you do lose power and now all of a sudden you're turning to your phone, one of the cool things is our station live streams our broadcast during these severe weather systems. So you can download the CBS 12 app, you can download the weather app, you can go to our Twitter, you can go to our Facebook, or you can just go to our website, cbs12.com, and you're going to find our live stream on all 5 of those platforms. You'll just click the button that says live, whether it's on the app or the Facebook or Twitter or our website. Obviously, Facebook and Twitter, we're going to pin them at the top of the pages for you. And you'll be able to watch our broadcast live on your phone, on your tablet, whatever device you may have. Whenever we have breaking weather situations, it is all hands on deck. Because you lose power in your television doesn't mean that we stop trying to get that information out to you. We're utilizing every platform we have to make sure you have the ability to access us.
Thank you. I appreciate it, and I make sure to get that plug in there for you. Is there a practical value to naming weather events such as what the Weather Channel does? I don't quite understand.
You're referring to winter
question.
storms. They're referring to winter storms. You know, what's funny is this happened back in 2015. And I know that because I was still in college. I was a senior, and I went to a weather conference in Atlanta, and the Weather Channel, which is headquartered in Atlanta, had a panel talking about how they were going to name winter storms this upcoming season for the first time ever. And that room was packed because so many people were so upset that a private entity, not a weather-related entity like the Hurricane Center, like NOAA, whatever, was doing this. And I will tell you the kind of consensus from the weather community, there are still some that don't like it, but I think it is really toned down from 2015. People were against it, 2015, 2016, even 2017. But I think what we've learned with these private companies, and AccuWeather does it now, unfortunately, they do it a little bit differently, and I don't care for theirs as much as the weather channels. I think the bottom line is if something's named, people are paying more attention to it. And they do have a list of criteria. Not every storm is going to get named. You have to have so many millions of people under a winter weather alert. It has to produce this much amount of snow or this much amount of ice, whatever. So I think the environment has changed around what people, consider that. I think nowadays a lot of people are realizing it is getting the weather information out there. And while a lot of people were mad that it wasn't a national or a federal program that was doing this, like the Hurricane Center, like NOAA, like the Weather Service, it was a private entity. I think we've all kind of come to the conclusion that we're still all on the same page. We are getting breaking weather information out to the general public to save lives and property. That is our job. And I think nowadays, a lot of people have finally come around to it. There may still be a few holdbacks, but it's not as controversial as it once was.
Well, I have one question that's mine. How do you like being in the middle of the storm when you're trying to update whatever media you're working at, whether it's your app or your station in you, and you're in 120, 130 mile an hour winds or whatever the circumstance finds you? I imagine that's something you like or don't like.
Oh, I love it. I live for it. I used to go out a whole lot more. I don't anymore. I only go out for really major events because I am the hurricane specialist now. So what I do at our station is I work a lot more at the station than I do inland, or outside, I should say, in the actual storm. But if a storm is threatening Florida, I will be outside and I will put myself in the worst of it than anybody else, because I, as a meteorologist, as much as I love our reporters, can give you a better context of what is happening versus a reporter that may say, look, this stop sign's blowing around. Look, this trash can flew down. I can give you more of that meteorological. We are in the eye wall. This is going to last for several hours. Here's why this is, and bring a more impactful view at the worst of the storm. And that's what people like to see. Now, when I'm out there, I'm not doing anything but reporting. I have a weather producer back at the station that's getting my graphics ready. I have my iPad so I can see my graphics, but they're driving the ship. So I am simply out there. I'm protecting myself. My crew's being protected. We're never putting ourselves in harm's way. We have a contingency plan to get out of the worst if we need to. But when I'm out there, I'm not updating the app or the website or anything. People are doing that back at the station. My sole job is bring what is happening out there to you guys.
Well, all I can say is I found it very informative, interesting, and I'm glad we made it through the whole presentation. I'll now look at weather in a whole different way. Sheila, Jerry, you have any follow-up you guys want to do? No, we're good. Anybody have any more questions? Because
it was really very, very informative.
You got a couple of nice, very comments from the audience. We greatly appreciate it. Just as I've said, Zach, thank you kindly. It was a great presentation. And by the way, your dog has been having a great time walking around your couch.
He has been
under the covers. I think he thinks a storm is coming because he's been under the covers, on top of the covers, under the pillow. He's been having a good time back there.
Well, here's the thing. It's 8 o'clock. And so I normally go to bed at 7. So he's wondering why we aren't in bed yet. So I need to walk him down to the master bedroom, and we'll get to bed after this because I've got my 2 a.m. alarm ready to go.
All right. Well, we won't keep you up any later, and all we can say is thank you very much.
Thank you, guys. Have a good one.
Have a great day.
Thank you.